I'm going to talk about the benchmark variational calculations of small atoms and ions in the context of theoretical spectroscopy. All right, so let me first of all, give credits where they're due. Most of the data processing, most of the calculations for this work were done by Said Nassiri, who is a postdoc with me. Also, active participation was by Ludwig Adamovich from Arizona, and in some parts of this work, we also collaborated with Monika Stanke, Andrzej Kedzierski from Torun, and finally another group member, my group member, Jan Liu, also did some data processing. Okay, so our interest in studying few-electron systems is motivated by providing data for various applications, and that goes as far as to astrochemistry. Needless to say that atoms have spectra, and these spectra can be thought of as fingerprints, signatures that can be used to identify them in outer space. Even though small atoms have been studied since the birth of quantum mechanics, and qualitatively they're well understood, their structure and properties, but usually high precision studies of small atomic systems concern only a few lowest states. This is maybe less so for helium and lithium, but if you go to larger systems, then Rydberg series of states is not something that you would see very, very often. So we are trying to fill this gap to provide the data for Rydberg series of states. We've already had a couple of talks in this conference where people demonstrated applications of high accuracy calculations of atoms in determining various physical constants, nuclear charge radii, and things like this. So that could be another application. And finally, last but not least, we aim to provide some reference data for other types of calculations that are perhaps less costly, but at the same time less accurate. Okay, so our systems of interest, they're small atoms, so they have small z, and the product z times alpha is a small parameter. So I guess the most practical approach to computing states of such systems is based on the perturbation theory. So we first we solve the Schrödinger equation for the non-relativistic system, and then use the perturbative expansion of the total energy in terms of the fine structure constants and find corrections to the energies. These expectation values, E relativistic second, EQED third, and so on, these are expectation values of some effective operators that are well known. For example, the relativistic Hamiltonian, the bright Pauli Hamiltonian, has several contributions that are commonly referred to as mass velocity, Darwin, orbit-orbit, spin-spin, and spin-orbit. You can attribute to certain physical effects to those if you wish. I have expressions for them there. They're a little bit long, but they're well known. And the good thing is that we can calculate matrix elements with Gaussians for all these operators. So I will skip them because it's just a lot of formulas. As the mass of the nucleus in our calculations is not infinite, the very first thing that we need to do in order to treat small atoms is to separate the center of mass motion. This can be done in various ways. Ours is not unique, but I guess this is one of the most straightforward. We introduce relative coordinates. We put one particle at the new reference frame, and we refer all other particles to this reference particle, number one on this picture. So then you have this set of n-1 where big N is the number of particles, small n is n minus one coordinates, and the center of mass coordinate. And then the kinetic energy operator separates into the two contributions. And essentially, after this, we concentrate only on finding this internal wave function, right, that corresponds to the intrinsic motion of the system, and that such states correspond to discrete spectra. Okay, so we use the variational method, standard Rayleigh-Ritz approach, where the wave function is expanded in terms of linear combination of some basis functions. We've already seen a couple of talks with applications of Hiller's basis set. Here we use different type of basis functions, explicitly correlated Gaussians. Gaussians because they all have some quadratic forms in the exponents, right, that depend quadratically on all interparticle distances. And here T means transposed. R, big R, oh, sorry, small r is the vector where you have coordinates of all internal coordinates stacked upon each other. Another thing to notice here is that these basis functions have matrices here, 3n by 3n or n by n times Kronecker product identity matrix of nonlinear parameters. And these, I will talk a little bit more about them, can be optimized in calculations to obtain the best possible energy. So here I give examples of basis functions that are relevant for calculations of states with different angular momenta. These are S states Gaussians. This is for P states with odd parity. Then you can have if you have a state that where the dominant electronic configuration comes from 2 electrons in P states, you would need to use such functions, depending how the angular momentum of those electrons couple. And you can go in further, consider F states or systems with 3 particles in this non-zero angular momentum, and so on and so forth. It becomes progressively more complicated, but in principle, it's doable. It's doable. All right, so then of course we need to ensure the permutational symmetry of the basis functions. As long as you don't deal with spin interaction explicitly, you can get away using the spin-free formalism. Essentially, what you need to do, you need to apply certain symmetry projectors to the wave functions. There is a simple, very straightforward procedure that you can build these projectors for an arbitrary number of identical particles, electrons. In fact, in the calculation, this is all done automatically. These symmetry projectors are built. They're not written manually. They're built based on the total number of particles and the symmetry projector here. Okay, so so when these symmetry projectors act on basis functions, Gaussians, essentially it's equivalent to a similarity transformation. So all matrix elements would be computed in exactly the same way, no matter what is the permutation operator that is applied to the basis function. All right, and so the last thing that I want to say about the basis set and the explicitly correlated Gaussians is that I already mentioned that they have these matrices of nonlinear parameters that need to be optimized in order to obtain accurate solutions to the stationary Schrödinger equation. And unfortunately, this cannot be left. You cannot choose them randomly. You have to optimize them, right? So there are some strategies that allow you to do it efficiently. Stochastic selection, so-called stochastic variational method. That's what we adopt in our calculations. But in addition to this, we also use the analytic energy gradient that allows us to optimize parameters in a more efficient way by computing the energy gradient with respect to those parameters in a more efficient way, right? So basically, at a very small cost penalty, we can calculate the energy gradient basically in a single calculation. All right. So so what you need to, in order to enable this analytic energy gradient, you need to evaluate the certain derivatives of the matrix elements of the Hamiltonian and overlap with respect to the non-linear parameters. Now you see that this matrix AK, which has to be positive definite in the calculations to ensure square integrability of the basis functions, it's represented as a product of two triangular matrices. So that ensures positive definiteness in the calculations. Okay, so another thing is that if you notice these operators that I showed previously, right, for the relativistic corrections, you see delta functions here, 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 and in the previous slide. So they appear everywhere. You also have operators such as p to the fourth power, momentum to the fourth power. So unfortunately, these operators show the expectation values of such operators show slow convergence in calculations due to their singularity, right? Delta function obviously resonates with the term singular, but p to the fourth may not be obvious why is it a singular operator, but this can be easily seen if you apply p to the fourth to, let's say, hydrogenic wave function. You would see immediately that delta functions will start appearing there. So it's also a singular operator. And the problem with singular operators is that when you evaluate expectation values with them, the wave function is not sampled uniformly, not uniformly, but globally in the entire space. So that leads to a loss of precision compared to the energy. Typically, you would expect to get twice fewer number of converged significant digits when you calculate expectation values of such operators. But fortunately, there's some prescription how to deal with this situation. Actually, there are several prescriptions, but one of them is due to Drachmann, and that's what we use in our calculations. We apply it to compute the expectation values of the delta functions and also the mass velocity operator that involves momenta to the fourth power. And actually, one more maybe comment that in realistic cases, it happens often that these inaccuracies due to the singularity of the operators that involve in the relativistic and QED corrections, they largely cancel out, but not completely. So it's still better to use some sort of regularization technique to compute the energies. All right, so since most of my talk is about the oscillator strengths and transition rates, so here is the standard formula for the oscillator strengths. You see that the dipole transition dipole moment matrix element multiplied by the transition frequencies. There's also this factor that may not look very familiar, but this is due to the, basically this formula is the generalization of the oscillator strengths for systems with finite nuclear mass. Because in our calculations, we treat all particles on the same footing. So the nucleus is generally considered to be just another particle. And so this factor takes care of this, and it ensures that the sum rule for the oscillator strengths is fulfilled. All right, so yeah, so this factor actually is very close to 1, and it's exactly 1 if the nuclear mass is infinity. Okay, so let me show maybe a few numerical examples. The first thing that I guess we want to test is the non-relativistic energy, because there's lots of literature data on that, and also the accuracy of the non-relativistic function will define everything else, right? It will define how accurately we can compute relativistic and QED corrections, and it will also define how accurately we can compute the transition dipole moments. And there's been a lot of works. There's been a lot of large array of calculations for beryllium, mostly for the ground state, but here I quote a few recent ones, and you see that we essentially improve on our previous calculations by a factor of 3 to 5. depending on which state we consider. So for the beryllium atom, in this work, we consider 10 S states and 10 P states, singlet states. Yeah, so if you look at the uncertainties in the total non-relativistic energies for infinite beryllium, it's to my knowledge, it's the most accurate values today. Of course, the accuracy gets worse as you go to excited states, which is not surprising because the structure of the wave function is more complicated, and you need a larger number of basis functions to achieve the same accuracy, right? But because you're limited, there's a practical limitation. Maybe one naive question that one might ask, like how far can you go in these calculations? Can you calculate a state with principal quantum number, I don't know, 50? In fact, I know that some people don't even call this a Rydberg series unless n is 50 or 40. So there's practical limits. First, it comes from the fact that you need to increase the basis size progressively in order to keep the accuracy. And the second is more technical. At some point, using double or even extended precision becomes insufficient, and at some point you have to switch to higher precision calculations, quadruple or maybe even higher, because in order to describe electrons that have very different spatial distribution, right? So this is like kind of pseudo orbitals have very different spatial scale, and it turns out that it leads to some cancellations when you calculate matrix elements that involve matrices of nonlinear parameters. So in order to keep the accuracy, you would need to use higher precision. But apart from that, there's no principal limit on how high you can go when computing excited states. All right, so there's another table with transition energies. I show only a very small fraction of the data we obtain for obvious reason. I cannot show you tens of pages with transition frequencies and oscillator strings. But this one is for beryllium. Again, it's a transition frequencies that involve the lowest S state and P states. You see that the convergence, the accuracy of our transition frequencies is within a fraction of wave number when compared to the NIST atomic spectra database. Actually, one of the interesting things that we found that there is a discrepancy of about 10 centimeters for transitions that involve the 9p state. And I suspect that the actual reason for this, maybe there's some sort of a typo in the NIST database. I assume they store data in the form of Ritz energy levels, right, with respect to the ground state. And I suspect that the state 9p, because of maybe a typo, is about 10 centimeters off where it should be, because all the transitions that involve state number, state 9p are shifted by about 10 centimeters. So, and you see that, of course, as you go higher to higher excitations, the accuracy, well, it's maintained, but it's maintained mainly due to the fact that there is a cancellation of errors. Obviously, the wave functions become less accurate and the total energies become less accurate, but because we deal with essentially with the Rydberg series, the error that was accumulated in the error in the wave function in the core essentially cancels out. So the transition energies are still pretty good. All right, so here's another little table that illustrates the transition dipole moments. Again, I only copied a few numbers here just to demonstrate the range. For the ground state, the convergence is very high. The uncertainty that you can see is due to the truncation of the basis set, right? Doesn't include any uncertainty due to the possible relativistic effects and things like that. So it's only due to the truncation here of the basis. And you see that for the lowest transition, this quantity, the transition dipole moment matrix element, is very well converged to many significant figures. However, if you go up in the excitations for, let's say, this transition 10s 11p, well, it's not very accurate, even though the energy is for these states is accurate to about 10, relative accuracy is about 10 to the minus 7, 10 to the minus 8, right? So obviously the reason for this is that this external, the Rydberg electron part of the wave function is very basically changes very significantly as the energy changes, and that obviously affects the overlap between the S and P wave functions. And even though the energies are relatively well converged, the dipole matrix elements are not so well converged for highly excited states. Okay. All right. So, and then finally, oscillator strength. The situation here is somewhat similar. Also, for the lowest transitions, the convergence is much higher, as you can see, to many significant figures. In fact, in principle, you can discriminate here between various isotopes. Here I show the results for beryllium-9, but we also did this for lithium. In principle, we can talk about discriminating between different isotopes. To my knowledge, there is no data as of yet, experimental data that allows you to do that is accurate enough to distinguish between different isotopes. But maybe in the future, someday it will become possible. Yeah, so you can see that here the
you are already 6 minutes or 5 minutes.
Okay, I'm pretty much done. So let me just show, instead of giving you a long array of numerical data to look at, maybe it's easier just to look at this heat map of oscillator strength in the logarithmic scale. This is for lithium. You see that the highest values appear here on the diagonal. So that means the transition between NS to NP. But then as you go off the diagonal, it gets the absolute values decrease by orders of magnitude. In fact, here it even appears that there is some sort of valley. There's a mountain ridge right here and sort of a valley above the diagonal. Again, I guess it's related to how the wave functions of different states overlap. Same heat map for beryllium, and qualitatively the same behavior. So the oscillator strengths are maximized on the diagonal for the NS and P transitions, and then they decrease rapidly as you go off the diagonal. All right, so just one more slide here. This is a comparison with the experimental values. Unfortunately, as of now, the experiment is not very precise for the oscillator strengths, so it's a little bit difficult to distinguish between previous theoretical calculations and the newer ones. But I can tell you that for other, where was it? Here, for other transitions, there is quite a significant difference between what we compute in our approach and calculations that were done, for example, by Fisher with multi-reference Hartree-Fock. Sometimes the difference are about 5% or so. All right, so with that, let me conclude. In this work, we performed calculations of Rydberg series of states, S&P states for lithium and beryllium, and obtained accurate values of the dipole transition dipole moment matrix elements and oscillator strengths, and also found an error in the NIST ASD database. There is if you want to look at the tables, they're available in this publication. The data for lithium is still in the process of review. thank you very much, and apologize for
Fantastic.
taking a little bit longer.
Questions? Pardon.
Yes, thank you for your talk, Sergey. Did you do calculations in the velocity gauge as well as the length? And the second part of the question is that there are analytic relationships between the expansion coefficients in powers of the reduced mass mu over m, which provide a very stringent test of the accuracy for the finite mass corrections. And so this is an additional test that you could use in testing the accuracy of your calculations.
Okay, yeah, so I'm aware of, yes, that there is another way of doing this. So far, no, we haven't tried it, but you know, that could be probably a good thing to do in the future, but not as of yet.
For the questions?
I have a very simple question. I understand that energies are relativistic and the dipoles are not.
Can you please repeat, because I think I missed the first part of the phrase.
I understand that variational energies are non-relativistic and occur with relativistic corrections and transition dipole moments without relativistic. Am I right?
Okay, so very good question. Very good question, because I think the way how, if you want the sum rule to be valid, the transition, where is this formula for the, yeah, the transition energies have to be purely non-relativistic here, right? You can correct it for the finite mass, but the transition energy should be non-relativistic. But I think so. Maybe some people would disagree with me. But if this is to be used, you know, to calculate transition rates, to actual transition rates that can be compared to the experiment, it probably makes sense to use relativistic energies. Of course, we are still going to be missing the relativistic correction in the matrix element, right? But I would still think that this would make sense. So we actually did this, but to be honest, I wasn't even exactly sure what would be a more not a systematic, but a better way to present this data. So
Let me answer that. Yes. It would be much better if you include both relative correction to the energy difference and to wave function and to the liquid dipole moment. So then your result will be consistent.
Yes, I agree, but it's a little bit more complicated to do it here, because
let me finish also with my comment. When you compare it to some other calculation, it's always better to cite his more recent result than the older result, because we present your most recent result, but someone's older result. It's better to keep consistency with comparison. Good. And maybe other...
Okay.
Sergey, would you like
yes.
to comment?
Regarding the most recent results?
I mean, there are papers of others which are more recent.
Yeah, so maybe I missed it. If I did, I apologize. But I think that you're talking about this table. This table?
No, for the energies, yes.
Yeah, perhaps I might have missed. So you're probably talking about actually your calculations, right? With Mariusz. So maybe somehow I, yeah, indeed, didn't use the latest numbers. Sorry if I did so. Sorry.